Hello, everyone. GM. Sorry for the delay. I was just fixing the, the lesson content. It was like messed. I guess I copied things double last time I reviewed this lesson, but now it's okay. Just clone your repository again. Just uploaded that. We're going to pick lesson 18 today, learning more about gas limits, loops, optimization. We're going to learn new things about the EVM today. Okay, I do have a small review of 2 minutes for the last session. And I also wanted to clarify about the recordings. I was checking with Encode team today. They are moving for a new office. Okay, so today, tomorrow, maybe until the end of this week, they might have some delays. Expect maybe a couple days or 1 day of delay for each video recording, but then they are going to resume everything by the next week or so, okay? If you missed the first half of yesterday's lesson, because of the time zone change, you might need to wait an extra day for us to uh, have the recording for you to cover everything, okay? Sorry about that. Not ideal, but we should have those recordings. Okay, so if you just arrived, good morning, good afternoon, good night. We're going to start with lesson 18. Please update your GitHub. I just pushed this commit here. The lesson was like not this one. Wait, where is the commit? I have just pushed it. Lesson 18. Huh. I have just pushed the commit. I don't know what's happening, but I have. If you pick your Git, let me make sure I have committed that though. Yes, committed today. Okay. Yes. So before, for some reason, I had things uh, duplicated. Like there is the lesson example here, and in the bottom I put the same lesson examples for like it was messy here. I don't know what happened. In today's README, if you have the correct version, it's going to be like that. That is the lesson content, and that is a to-do here. Where it is. That is a to-do. Yeah, here. And we're going to complete this today, explaining the lesson. And then at the end, I should have the solution. And that's it. Okay, no duplicates or everything. This should be the correct version for today's lesson, okay? Sorry about that. I should have checked that before, but now it's correct. We have the proper flow for this lesson, okay? Good. So any questions, please let me know, raise your hand, tell me in the chat. I'm going to review for 2 minutes briefly the last thing we did in yesterday's lesson. We were doing this challenge here with OpenZeppelin, with the Ethan out from OpenZeppelin to learn about smart contract security. And we were completing this challenge. We put this smart contract on Remix, but you could also do with scripts, with your hard hat, local network connected, your local development connected to a public testnet. It would work, okay? You could put that in scaffold ETH. It would work too. You would be able to interact with that smart contract. And we did this one transaction here. I made a transaction transferring from my address to this other address 21 tokens, 21 decimals of these tokens. Look here. And I only had 20. So what happened, if you paid attention yesterday, if we subtract 20 minus 21, we don't have -1. Okay, this is Solidity version 0.6. So what we have is F, the highest number. Let me show that. We have now a state change, changing those balances inside the smart contract. So the balance of this address changed from 0 to 21 correctly. And the balance from my address changed from 20 to bazillions of balance. This could be a hack, could be exploit. This is a security flaw that happens in older smart contracts where they don't check for overflow. And the same way that we saw this security problem happening with Ethernote, you have a lot of different challenges here for you to explore many other security problems that might happen in smart contracts, okay? This is a conclusion from yesterday's lesson. Did you have time to play along with this? You didn't have the recording, so maybe you wanted to kill some time, 1 hour of the time, maybe you play a lesson or two of Ethernote. Ethernote.openzeppelin. It's given 404. What? That's great. Maybe if I see a question there in the chat, maybe it's because your browser cache or something like that. I don't know. If you put your MetaMask in Chrome, maybe it's going to work. Test it out. But I have it here, ethernote.openzeppelin.com. Maybe it was a typo. Let me see. Yeah, I guess there is no typo. Well, I don't know what's going on there, but you should be able to access and play the game. That would give you content trails for studying smart contract security. Okay, we are not going to cover it that much in this bootcamp, but now you have something to work on your weekend or after the bootcamp for learning smart contract security. Okay. Good. And if you ever need assistance or if you want to troubleshoot about these lessons, even though we didn't about these lessons or this challenge, even though we didn't cover them entirely in the bootcamp, please feel free to reach out, open GitHub issues. It's going to be nice to collaborate and to guide you through this path. Okay. Today we're going to see a piece of the EVM about gas limits. Tomorrow we're going to see randomness. Next week we are going to see scalability, DeFi. So all of those are different paths that eventually you're going to explore by yourself. You don't need to master all of them in a month or something like that. You can put them in your roadmap. Some of those you can pay more attention. Some of those you can pay less attention, deprioritize depending on your career, on your interests. So feel free to reach out in the future for each of those. At some point, you're going to pick a favorite topic, a favorite subject, or a favorite combination of subjects, and you're going to discuss that with your team. And then you're going to start ideating in your final project. Okay. Maybe you're going to enjoy more about DeFi. Maybe you're going to enjoy working with smart contract security. Maybe you want to build dev tools. Okay, so at some point you're going to pick some favorites. Today, I'm going to start another subject that would be understanding the EVM, about the amount of computation that we can do, the amount of work we can ask the EVM to do by understanding this property of gas limits. Okay? There is a security problem mapped in the article for Ethereum smart contract techniques that would be denial of service with the block gas limit. Okay, so it is a little about closely related about smart contract security too. Okay, because when we start doing programs in the EVM, in smart contracts, like ballots, like games and all, we often think like normal programs that we do with C, with Java, whatever we do in a computer, like JavaScript and all, where we can do anything. But in blockchains, we have limits of the amount of processing that we can do in one transaction, either for deploying a smart contract or for running operations. Okay. So it is related to security too. It can be a denial of service. This kind of attack can be malicious player blocking your smart contract from operating, or can be a naive implementation, can be a flaw from the developer that didn't pay attention for this specific case, and it happens. Let me bring you a paper, demystifying loops in smart contracts. It's getting very dated, 21. Couldn't find newer versions of this paper, but these people, they took 20,000 solid smart contract deployed on the Ethereum mainnet to study the loops that they were implementing, and what kind of technique, arrays or simple loop, unbounded loops, and now it's not much of the security part. It was more like a summarization of the practices and all that were being applied. And the conclusion that they had is that there are many loops in the blockchain, not like a security consideration, but they saw a lot of specimens, a lot of instances of these loops being deployed on the mainnet. And by itself, it's not a big problem. That is a possibility of using a loop in smart contracts. It is a valid function. It is a valid operation. We even saw a loop in one of our smart contracts. Don't know if you paid attention, but if you pick the construction function from the ballot, there is a loop there. For every member passed in the array of the parameters in the constructor, you're going to create one proposal in that batch. So this is a loop. This is going to consume gas per operation. Okay. Do you remember about this gas optimization part that we saw, that every new operation is going to add a little more of work? We would write a loop, and the more work that we would do inside that loop, operation by operation, it would increase the gas limit, the gas cost of that transaction. Okay. Well, we saw that yesterday, and we even saw ways to optimize that. But the problem that we're going to study here is that whenever we have a for loop like this, for every user, do something, for every item, do something, for zero to something, this is an unmitigated disaster. And most of the smart contracts are implemented like that. The problem here is that these loops are going to work. They're going to consume some amount of gas, a few thousands units, 100,000, maybe 1 million, 2 million units of gas, and they're going to work. Let's say you're doing an auction. You want to put an NFT for sale, and then you are going to receive bets, or any entries. Eventually, this bid period is going to end, and then you need to loop through all of the bids to pick the higher price. Or you want to loop all of the plays in a game to see who's the winner. Or you wanted to sort through a lot of entries. We speak a lot about sorting as an example. Okay, TLDR, do not sort. There are better ways to do that. This is a problem because of gas limit. The more work we do, the more gas we're going to consume. We know that since week one. The Ethereum virtual machine is running on the Ethereum blockchain. And every time we're going to do a state change, we need to pay for that state change. So that in the first lesson, more of that in the second lesson. This is the reality of the Ethereum virtual machine. There is no way there's no bypass here. There's no workaround. This is how the EVM works. If the EVM wasn't like that, if we could do any kind of arbitrary operation without paying or without limit, Ethereum would simply crash. In next week, we're going to speak about the scalability effects, like the scalability to LLM. And now there are blockchains that can process much more transactions. but there are some implications. Speaking about Ethereum only today, Ethereum would crash, would get cog, all the transaction would be throttled if someone would be processing something for a long time. Ethereum is a shared resource, like all of those blockchains are shared ecosystem. So if you're using that resource for a lot of time, no one else can use. Like roads. If there are a lot of trucks going through a road, you need to wait for you to go with your car, right? So if there were billions of huge transactions being processed by the Ethereum voting machine, Ethereum would just clog and no one else would be able to use it. So this is why they implemented this limit. It's designed like that. You need to pay for computation. There is a limit of what you can process and all. And this is a network property called block gas limit. It is voted by the miners. Since the update of proof of stake is voted by the nodes doing the staking now. You cannot tweak that in a transaction. Currently, there is no way to do a transaction that would exceed the block gas limit in the amount of gas. Let's look on the Etherscan for us to see the history of this property in Ethereum blockchain. Okay, there is a resource here for charts and stats. One of the charts that we can pick is the block limit, gas limit in the block. Okay. And this is the current state of things. We have a fixed limit of up to 30 millions. Long time, they just bumped it to 36 a few months ago. And this is something agreed by all of the miners. The problem here with the thing that we want to study in today's lesson, the problem here is that this is relative to the amount of computation that you are doing. So for example, if you are deploying a very big smart contract, a smart contract that is running like Doom on chain, a very big smart contract doing a lot of operation, this is simply going to fail. You're going to try and deploy, it's going to fail, your smart contract is too big, and then you go back to engineering, to design, because you cannot deploy it. Or you wait a few years until they bump the gas limit again, and then you deploy a smart contract. It's not ideal. Ideally, you're going to pick a smart contract and you're going to cut some features out of it, okay? Or you are doing a very big transaction, for example, a lot of swaps, you're doing a lot of trades inside the same transaction, sending a token here, collecting from other places. Now you try to send a transaction and it doesn't work. So these kind of errors are the less catastrophic errors. You send a transaction, they fail, and you go back home. Not much damage done up to this point. The problem is when the system is working up to a point, it's working for a few months or a few years, and then suddenly stops working. Let me give you one example. I guess the article, this article mentioned that whenever, for example, we are distributing dividends, they mentioned that somewhere. For example, you want to send all the user dividends. Let's say we started a company. We are all shareholders. How many we have here? 38. So 38 shareholders. It's excluded the AIs, maybe 30 something, 30, let's say 30 shareholders. And every month we're going to have some profit, and we're going to distribute this profit with all of the shareholders. So we're going to draw a loop from 0 to 29. We are going to divide the profit by 30s, and then we're going to send all of them, right? This would be an operation at the order of 30. So if I spend 10,000 units of gas per operation, it's going to be 300,000 for computing the whole thing, right? Eventually, we are going to add more shareholders. We're going to do crowdsource, we're going to do an IPO or something. And let's say we have 1,000 shareholders. Each operation is going to be 30,000. Let's say 1,900 shareholders. So to do all of this dividend distribution, we are going to spend 29 millions units of gas. This is still possible. We have a limit of 36 now. Okay, good. So with 29, it is still good. But let's say we start getting more shareholders, 1,000, 1,100, 1,200. Eventually, when I want to send all of these shareholders a dividend at the end of the month, what's going to happen when I hit this limit? Because I have a loop, the more operations that I want to do, what's going to happen? Ideas? You see the problem evolving here? It's going to revert everything. It's going to revert everything. And the contract is blocked forever. It is a denial of service. I can never distribute dividend again. Because even if I kick a shareholder for some reason, they would be very mad at me, I guess. But for some reason, I would decide to kick a shareholder just so that I can distribute the dividends. There is no way to run that dividend because I still need to distribute the dividend for the past month, right? So the contract is clogged forever until we convince all of the miners to increase the block limit again, which may take 4 years, 3 to 4 years, like this period that happened here. Okay? Every time that we increase the block limit, we decrease decentralization. We make the nodes a little more difficult to run. So a common Joe trying to participate in this blockchain would need to have more capable hardware for participating. So this drives decentralization. This drives centralization effect, actually. Lazimi, you want to ask something?
Yes, I have a question. Is there an example of the contracts that on the mainnet, for example, that are blocked forever?
I don't know any specific contract that was denied by gas limit, but I do have an example that we're going to cause today. I'm going to implement this smart contract, and we're going to see it fading. We're going to do more and more operations in sequence, and we're going to make that smart contract fail, okay, because of gas limit. And then I'm going to show you how to fix that. Okay. Okay. This is something that very rarely happen. It is an unmitigated disaster. So all of the smart contracts that you interact, that they would have a loop there, that is a danger. You could be using that normally for years. For example, you're crossing a bridge. There is a danger there. If you put too much weight on it, it's going to break, it's going to fall. But even though we keep crossing that bridge, because it's a calculated danger, okay? So all of those smart contracts out there in the blockchain, in the mainnet, they are in danger. If you put too many members in that array, they could fail. It is an unmitigated disaster. But even though we can keep using them, okay? The purpose of this lesson is so that you know this, so that you design smart contracts that they are protected from this risk, and that you understand more of how the EVM works. Okay. The problem statement is clear before we start doing the solution. I can show you this example of creating a big transaction, making it fail with example of a bubble sort, okay? But I want to do a disclaimer. Do not sort on chain. There is a clear indication for that. Whenever you want to pick like the the biggest entry in array, like the highest bed or the largest amount from liquidity provider, something like that. You might be tempted to sort them and then pick the first, the second, and the third position, right? So this is not a very good way. This is very normal for you to do in databases, in normal programs and all, but this is not very good on blockchain environments, because you do need to go through all of those records. Sometimes you are going to have n squared operations. So it works with 10, it works with 20, with 50, but when you go to 100, to 1,000, it totally blows up. It's exponential. Okay? So it can cause problems. We're going to see how to solve that. Okay, so let's do this bubble sort example in Solidity by implementing this sort. We're going to create a big transaction just as a visual example, but later you can extrapolate that for any normal smart contract that you're going to be doing, okay? Do not sort on chain, I told that already. It's more about dealing with loops, okay? So it is a sorting algorithm that in the worst case is going to be at the order of n squared. So if you are sorting like 10 members, you are going to do 100 operations. Okay? And in the best case, you're going to do 10 operations. So it is okay. It's not the best sorting algorithm out there. It's not about efficiency here. It is about solving the gas limit, removing that limit, that ceiling that we have. Okay. I'm going to explain this algorithm with this GIF in a while. I'm going to show how to implement it in a smart contract with a project, and then I'm going to do a script for running it. So for the next 20, 30 minutes, we're going to understand very well how that smart contract works for creating that big transaction. Okay? We won't use this big transaction as an example. I'm not going to use ethers. It could work. We have ethers from yesterday. Some of you missed that part. We don't have the recording yet. So let's return to VM normally, but you know that you can use ethers for all of this. So I'm going to pick an old project, for example, project 5 that I have here in my computer. I'm going to copy all of these files. We did that a few times in this bootcamp, right? I don't need the contracts. I don't need the whole thing. In fact, I don't even need my .env for today's lesson. I can just copy the structure of this folder, and I'm going to create a new folder. So let's name it gas limit or whatever we want to name it. And I'm going to paste these files here. Sorry for the white background here. Eyes hurt. Mine would hurt too. It's just because my computer is not applying the theme to my folders. But this is the structure that I have. Those files here. I'm going to do an npm install, and everything should work out of the box. Okay. Dante, you have a question here?
Yes. So node modules, contracts, and what else that we can omit?
You can copy all the files without the folders. If you copy the folders, there's no problem. It's just that I'm not going to use the past contracts. I'm doing that just for the sake of organization. But you can copy all the files, and then you do npm install. Things will work. Okay. And then I'm going to create some folders again, like make dir, contracts, test, and scripts. I want those directories. Now I have them here. Okay. People, it's the same thing as copying the folders and deleting the files inside the folders. So instead of copying contracts, scripts, and tests and deleting the files from inside these, I can copy just all the files without the folders and then create the folders from scratch, blank, okay? Yvonne, basically it's a new project generated with npx hot in it with VM, okay? Everything from today's lesson would work with ethers too. You would just need to adapt. Here using VM as we have been using the past lessons. Works like a charm too, okay? So you can pick your project 3, project 4, project 5, copy the files here, or you can start from scratch. You install hard hat with VM, both would work, okay? Which open this on Cursor. I updated Cursor this weekend and sometimes it's lagging a lot. I don't know why, what I did wrong. Sometimes it just freezes and then returns. I guess it's a problem with the specific version that I have. But again, for this bootcamp, I'm using Cursor just like I would use VS Code. So don't bother with the differences, okay? Dante, you want to ask a follow-up question?
No, I just want to make a comment. Like that, I've actually um read one of the limits for VS Code and Cursor, or one of the issues was that it tends to run slower because it's kind of like lagging your computer, and like that was one of the selling points for Google's IDX, um, which is cloud based.
Yeah, if you run it in the cloud, it's even better. You have a separate environment for this. I couldn't notice any difference from VS Code to Cursor so far for almost uh, I guess I've been using that for more than 6 months now, but this is the first time I'm having problems with it. Don't know if anyone else is having, but it just freezes sometimes. I hope it's not going to happen today. I will try and fix that the next weekend. Okay, so some people sometimes ask why I'm using Cursor. Well, I would suggest that for students, because you can ask about things using the context of your lesson. For example, I'm using this lesson here, and I can ask why should I avoid sorts. And if I ask this with the context of this project, it can read the whole README and things, and it can help me to answer this question. Actually, I'm asking the wrong place. But yeah, you got the point, right? So this can help you to study. Okay, if, for example, all of those issues that we are asking in GitHub, I have the pleasure of answering them, not avoiding. Please keep asking questions. But I know that eventually I'm going to be replaced by AI. AI is going to answer all of these questions very easily and quickly. So this is why I suggest if it's helpful for you, it is great. Okay. Now let's start with the experimentation for today's lesson. I would invite you to create a contract. I guess I specify the name of this contract would be the sorted ballot. Yeah, I would invite you to create a file called sortedballot.sol. Which is like a mock. It is a example of a ballot contract, which we have a loop in the constructor. We have this loop there. And I'm doing the service of sorting the proposals alphabetically by name. I didn't include the whole remainder of that smart contract, just doing that part specifically. I'm doing the on-chain service, which I'm going to see that is totally useless today, but just as an example for gas limits, we are doing the on-chain service of sorting the proposals. So I'm going to go from proposal 0 to proposal maximum. I'm going to compare the name of those proposals. If it starts with an A, B, C, D, blah, 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 and then we're going to rearrange them in alphabetical order, okay? We experimented a lot with the ballot smart contract in this bootcamp. We know how it works. We know that we can pass an array of proposals. The first proposal is always the index 0. The second proposal is always the index 1. regardless of the name, and we don't use the name of the proposal for voting, we just vote on index. Here we are implementing a feature so that we can sort those proposals, okay? The algorithm that we are using here is a bubble sort. We have a while true. Whenever we see this in a smart contract, it's like it's almost like a crime. You can run away, run to the hills. But it can be used sometimes. But here we have a while true. We don't know how much of gas we're going to spend in this while true. And eventually, when something happens, I'm going to break. The condition is that if I went through the whole while comparing all the proposals and I didn't swap any positions, I consider that I can break. So this while can run 1 time, 10 times, 100 times, 1,000 times, 1,000,000 times until it breaks, and we don't know. You see the problem here, right? Let me open this GIF to explain. I have an array that is not sorted. For example, this array of numbers could be an array of names. And I'm going to pass through this array in loops from beginning to end several times. Bubble sort is not an operation that is intelligent, keeping track of the positions and considering that for the next loops. No, it's very dumb. I will put numbers in the incorrect position a lot of times. So it's more for the simplicity than actually for the efficiency here, okay? Let me restart from zero. So I will copy, every time I see a number out of place, I would copy the next one and I would replace them, swapping them one by one. I always swap the number before with the number after. So when comparing 6 and 3, 3 is smaller than 6, it would go behind. 6 and 1, 1 is smaller than 6, I would put 1 behind. You see how I misplaced the number 6 a few times? This is by designing the bubble sort. And when I reach the end of the array is not 100% sorted yet, but it's a little better than what it started. For example, the number 6 shifted to the middle, the number 8 shift to the end. So we have one number sorted there. Now we're going to start again. We compare 5 and 3, we would swap. We're going to compare 5 and 1, we would swap. Then we would compare 5 and 6, we're going to see that they are in order. This is going to be repeated iteration after iteration until eventually I have the whole array sorted in a very inefficient way. This lesson is not about gaining efficiency, it is about gas limit. So this is a great candidate for explaining inefficient loops. Okay. Imagine that this could be a comparison of bets, could be a comparison of bids, could be a game. Imagine any kind of loopy operation that you do here. Good. A question, Dante?
So how does it relate to gas limit? Is it to doing that process to control it, or are we preventing it? Yeah, or preventing it from hitting a gas?
We are just creating a big transaction for now. We are using this loop, it's a very dumb loop, just to create a big transaction. And then we're going to see it failing. Okay. So this smart contract that we have here is implementing bubble swap, doing exactly this operation from the first, from the second position, the first pair to the last pair. I'm going to compare these objects, the previous object with the current object. I'm going to compare the name of them, and it works. I guess I have this in the I have this in the documentation. We have bytes here representing those strings, and the byte equivalent of the string A is numerically lower than the byte representation of the letter B, and so forward. So it can be used like this. If I pick the number equivalent of the name and compare with the number equivalent of another name, and this number is higher than that number, for all of the alphanumeric characters, this is going to be a good sorting mechanism, okay? Not considering like accentuations and special symbols, just considering the letter of the alphabet, this is going to work. So whenever I detect that this is happening, okay, I have banana and then I have apple. I can swap those. I can save the next position in a memory. I can swap it like I had banana apple, right? Now I have apple apple, and then I'm going to have in line 25 apple banana, and then I account for the swap. I'm going to do 1, 2, 3, 4, 5 swaps all the way again and again and again and again and again. When I get to the end of the array, if I didn't swap a thing from the beginning to end, I can break. If I had some swap, it means that it might not be sorted yet. So I reset swap to 0, reset the index to 1, and start in the beginning again in a loop. Is this crystal clear for everyone? Sound like a complex algorithm, but actually it's just comparing numbers line by line, pair by pair. I want this to be clear for everyone because later we're going to rewrite this, and I have the solution in the readme too. So if this algorithm is clear for everyone, we can proceed. We have a script for testing that. Or we could deploy that in Remix and test that manually, which would take a while. So I'm going to create a script, name it what is the name of the script? I don't remember. So test loop can be a good name of the script. Test loop.ts or test guess limit would be a better name. And before we even dive into code, what we want is to deploy that smart contract sorted ballot, passing some ballot, some proposal names for that ballot, right? And then we want to call sort proposals. This is exactly what this script is going to do. We copy some parts of it first, okay? I'm going to, let me copy some parts of it. So what we want to do basically is this. Okay, and of course I'm going to copy the remainder. I'm just going to copy this just to explain first. So what we want to do is this. We want to deploy the ballot contract, okay, with some proposals, like we did in the previous exercises. And then we are going to call this sort proposals operation. We're going to get the transaction received, and then we're going to log. We spend this much gas in this operation. Okay, but there is a little more complexity. Instead of composing those proposal names on the fly, I'm going to use a package called random words. I have it here in the documentation too, which is just basically a dictionary of words with a random number generation that I can ask it needs to be this version, okay, 1.3. The version 2, the recent version has some different implementations. It has to be this version. So with this version, I can ask it to generate, for example, 5 random words, and it's going to be like this. Random words with a minimum of 3 and maximum of 10, exactly 2. So it is going to be a database of words for us, just so that we don't need to create these words ourselves, hard coding. To install it is very easy. I can run this command, npm install save dev random words at version 1.3. This is a JavaScript library is not going to be used in production or anything like that. It's just for us to run that script or suggesting random boards. And then we're going to implement it inside the script in this line. We copy the whole string script. It's going to be implemented in line 10 to generate a word database. Okay. And I'm also going to do a loop in this script by starting with 100 words. We're going to incrementally increase. We are going to test with 100, 110, 120, so that we eventually break that smart contract. Okay, let me do ons first, without the for, without the try, to show, and then we put the loop again, the try the loop. I guess I have a problem with this proposal. Do we have a problem? Also, is a type of one. Yes, because I did not compile my smart contract. Yes. Yes, alerts me. That's correct. I guess I just need to compile. What? Oh yeah, I removed the .m for some reason. Let me remove that. I don't need William. Sorry, we got some configuration problems here. I don't need .m. I don't need anything of that. Let me just compile this. Don't know if you paid attention. I didn't copy my .env. Decided not to, but it caused me this problem here, and now I solved it. When compiling the smart contract, now the IntelliSense can know that the proposal is the prop that I get is of the type of 0x string address. So I'm going to have those proposals. We did an exercise about that in lesson 6 or 7, if I recall correctly. I guess lesson 7. 5, 6, yes. And we use that in description lesson 8 too. So we know about this struct. And I'm going to pass 100 words here. I'm going to deploy that smart contract with these random words. And then we're going to get the transaction receipt for that sort of proposals. And let's see how much gas we spend. Okay. Let me run this script. npx hat run script test loop.ts. I removed the loop in the script. Let's just keep the loop in the smart contract, doing one test with 100 words, so that you're going to see how much gas we're going to spend. We passed these words: night, water, spell, group, live, unit, made, all of these words which are not alphabetically ordered. We spent 17 millions units of gas, with 57.46% of the total block gas limit spent here. And we have these proposals sorted. We have these names sorted in alphabetical order, you see? So this is the example. This is the visualization of that sort script, okay? I'm going to put the loop again, because now I want to increment it slowly so that it reaches the maximum limit of block. What is the block gas limit? It's not 30 anymore. It's now 36 millions. Let's see if I got that correctly. Now the maximum, yes, is 36 million unit gas, a little more, a little less, but almost that. And then we're going to see how quickly we hit that limit. Okay, I don't know exactly what version of my local hard node is running. I guess it is the Paris version should have the increased block limit. We're going to test that right now. So we're going to start with 100 boards from this database. And loop by loop, we are going to take a bigger slice of this from 0 to 100, and then from 0 to 110, from 0 to 150, until we get close to 100% of the gas used. And then we're going to see what it happens, okay? So as we are closer to the limit, we're going to increment less of the word count until I know exactly the amount of words that we can sort using that script. Okay. This might take a couple minutes. In the meantime, you can take your guesses. How many words can we sort before we hit the guess limit? So we first started with 100 words. It used 47% of the block guess limit. And then we tried with 120 words, picking 20 extra words at the end. And then it used 26 million units of gas. So it uses 72.48% of the block limit. You see how a small change can be impactful. So we have trust guessing 135. We have Ulatsmir guessing 132. It is April's Fool, so I can say that there is $1 million prize for whomever gets that correctly. Of course. Just kidding, there's no prize. It would be a fun prank. Only 2 guesses? No one else is willing to play? So then we tested with 140 proposals. And congratulations, we broke the block limit while sorting 140. So I guess it would be something in that range. We stepped too fast here in that exercise. Let me try again with the new scoop. And you see the error, transaction out of gas. So eventually you run out of gas. You broke the block limit while sorting 140 words. Let me try again here. So with 120, and then we tried with 140. Oh yeah, I guess I should adjust this step. I'm stepping too fast in this loop. With 30 millions, it was easier. With 35, it's getting more tricky. But then we have this block limit. Nathan, you can run more times because depending on the dictionary that you pick, if you have a worst case scenario or best case scenario, the difference of computation is big. Okay, if you have more words starting with an A in the beginning, it's good, like this. If you have something more close, like accurate is the last word, this is going to take a lot of gas until I put that word back in the first position. You see, attention. So depending on your initial guess, the initial guessed, no, guess, no, yes, initial guess, the words that you have in the beginning, this operation can consume more or less gas. That is gas and that is gas, true, similar words. Tricky. Okay, is that clear for everyone? We hit the block limit. Can consume more or less depending on the luck that we have in the initial distribution. And then we could consume more or less gas, but we always have a limit. And if we recall from yesterday's lesson, we could apply techniques for spending less gas per operation. I could maybe increase that limit for 200, 250 words. 1,000 words, something like that. But I'll always have a limit, a ceiling of what I can do. Okay. Is that clear? Even if I make it more efficient, I'll always have a limit. So making it more efficient by itself alone is not enough. I will always have a limit. Okay. I want to remove that limit. I want to be able to sort all of the words of a dictionary. I want to do machine learning inside a algorithm. How to do that? Just kidding, never do that. It's just that it might be a big operation. Okay. Laurent, you want to ask something?
Yeah, when I try to do the same like you, it seems that I'm missing the artifact. So how are you supposed to get the artifact, by compiling or?
Yes, before we run any script, you gotta compile. I had that problem here too with this prop and all because I was missing the artifact. So you compile your smart contracts, you solve this.
Okay, thanks. Because it seems that when you don't have the artifact and you run the script, they say, oh, congratulations, you broke the block limit. And even if you input only 2 words, so it's a bit short for a test.
Yeah, if you run it with hard hat, it should compile your smart contracts automatically. For example, if I do an npx hard hat
No.
clean, if I do this command, I don't have the script anymore. So if I run this, it should first compile the smart contract and then run the script. Look here.
Okay. So what the clean is doing?
Clean is removing the artifacts from my folder.
Okay, so we need to, and I think I put my test loop in a test folder. Does it have an impact or no?
Oh yeah, you should put the scripts in the script folder. I know that we named it test, but it's not using Mocha or anything like that. It is a script. We are testing the smart contract with the script. Okay.
So it will have an impact, the place of this TS file.
If you run with npx hard hat test, it will be an impact. But if you run with npx hard hat run, there is no impact. I just recommended putting the script folder for the sake of organization. Okay.
Okay, thanks for your explanation. Thanks.
Good. Okay, so here we could sort 100 words, 120 words using 24 million units of gas. But even though we have a limit, so doing everything in one go in one transaction is not possible. Is there any technique that allows us to divide a transaction in 2 blocks? Start the transaction in block 150 and end that transaction in 151 or 152? You know of anything that would allow us to do something like that? Like I'm going to send a very big transaction. It's going to require 100 million units of gas to run that transaction. So I will need to process it through 4 blocks. Is it possible? No idea. Maybe I didn't explain that properly in the first week. Ivan, that's a very good point. It would break atomicity. Well, we can, all the blocks in the blockchain would take a previous state to a next state as a function of the transactions inside that block, right? So if we start a block in the first state and we keep 3 blocks working that same state update, we wouldn't have blocks in the middle, right? We wouldn't have a state in the middle. So those blocks wouldn't produce anything valid of state. Those incomplete blocks, they wouldn't produce anything valid as a state for the blockchain. So we wouldn't be able to compute a hash. So we wouldn't be able to broadcast these blocks, right? Because they don't have a final state. There is no way in any blockchain, in any chain of blocks, for us to have an unfinished state saved in blob or whatever that is going to be carried over for the next transaction without using, in fact, the state. The only thing that has persistence in a blockchain is state. Every time that you start a new transaction in the next block, you're going to have a clear picture of the memory. The memory is going to be all clean. You cannot pick the final state of memory in the last EVM run, in the last transaction, and use for the next. There is no memory snapshot or anything like that. You have to offset to state. Nathan, very good answer to a transaction through 4 blocks is not possible. There is no way to carry over the processing, the memory of a transaction through more blocks. So here, to solve this problem, so how to fix the contract? I want to refactor, since this was order of n, or order of n squared, it was a very big operation depending on the number of words that we have, the number of entries. I want to do a big sequential number of small operations. This is the fix of the smart contract, so that I can do 1/3 of these operations in the first block, 1/3 in the second block, and the last third in the third block, so that I finish this processing within a lot of blocks. This would mean that I would need to keep track of this operation progress. And for that, for having persistence, I will need to use state variables. In this example that we have here, we are all using memory variables. Let's pick the code. So within the loop, this line 19 defining this iteration, this line 20 defining the swaps. Within the loop, every time that I'm changing, I'm working with these variables here, they are in memory, so they are very cheap to work with. Whenever we go to use state variables instead, for keeping track of the operation progress within those different operations here, we are going to consume more gas. So this seems controversial. The problem of the current smart contract is that we are running out of gas quickly, and we cannot process all of these words without hitting the limit of 36 million units. So the solution is spending more gas. Seems crazy, right? And we're going to see that the conclusion is, yes, we're going to spend more gas per operation, per word sorted, per loop process, or anything like that. But at the end, we can transcend, we can skip that limit, and we can finish this operation without hitting the limit by using a lot of sequential blocks, okay? This is explained here in the article. How can we avoid get looping? So first thing, avoid source, like I said, sorting on chain is like a joke, and it's very difficult to justify doing that because you can always do that in the client side. Whenever you're looking up for lists, ordering lists, looking up for things, you can do that in the client side, okay? Every time that you have orders of n, of the logarithm of n, so you would have these problems, can be exponential. Use hints in the client side to find user carried and filter lists. So there are a lot of workarounds for you to skip loops whenever you want to return an array. So you cannot return arrays. We saw that in the previous exercise. So you can loop through them and dump the whole process from a call, but that could also give you gas problems. It would hit the gas limit. Even this constructor function here, people, that we have in the Solidity, it can hit the gas limit very easily. If we try to pass too many proposals, it can hit the gas limit just at deployment. So there are many considerations for that. When you need to do a loop, for example, distributing dividends, calculating the score of a game, doing the winner bid from an auction, whenever you do need to go from 0 to n dynamically, the only way to solve the problem of the gas limit is to work with granular functions that would return one item at a time or one part of the solution at a time while dealing with race conditions. This is a technique called amortization of work. You can do any kind of big operations. You can divide it to a lot of tiny, small sequential operations, every member of that loop and all. You can do a lot of small, tiny contract functions invocations at a time. And then when you finish this operation, you assemble all of these pieces, or you do amortization of work for assembling all of those pieces again and computing that all at once. And each implementation can't leave the state of the contract half-baked. You need to keep the contract in a working, acceptable state after each atomic operation. And then at the end, you need to combine it all and do the change at once, or have some migration period for you to do this change. Okay. Seems complex, seems a huge rewrite and all, but we are going to see with this example side by side how easy it is for taking this logic that is written in memory. Some things are in state, but most of it is written in memory. And we are going to rewrite it here, source proposals, for receiving some steps as parameter. And I'm only going to do like 10 steps at a time, 100 steps at a time, 1,000 steps at a time until I complete the whole process. Okay. Question here, Dante?
Yeah, so basically you're using the client to do more of the work because it has no constraints as opposed to the contract, right?
Exactly that. We should work with patterns that move the consumption from the resource that is scarce, in this situation, the EVM, to the resource that we have in abundance, that is a client. Okay. For example, you are at the end of an auction. You, the operator of that auction, you could charge like a fee for paying for your gas cost. You could go there, call that smart contract 100 times, pay for all the gas out of your pocket, and do that calculation at the end of this auction. If it's a game, all of the new plays in that game could do this calculation one step at a time. And at the end, the winner would pay for this gas because they want to claim that prize or something like that. You know, you would design this so that you remove this whole loop from the EVM, from the resource that is scarce, and you ask the front end or the back end to do 1,000, 100,000, whatever, tiny contract function invocations to complete that process. Okay. That's the concept. And we're going to visualize that with sort because it's very visible. But in the future, whenever you want to implement a loop, we can follow the same technique. Okay. Any other questions? Let's see. I see Arda, you are following. Naya, Gregory, Nathan. Okay. KB. Okay, Martin. Good. I have everyone else with your cameras closed. I can't measure your facial expression, but if you have questions, let me know. So anytime you have a loop that is an unmitigated disaster, if you feel that eventually you can have too many bets, too many plays, too many items, too many entries in that array, which would probably or possibly hit the gas limit, you can apply the same technique. Today I'm doing with the sorting smart contract, just an example. You know that you shouldn't sort on chain, but I'm going to show this technique that can be applied for other smart contracts in the future. Okay, so I'm going to name this contract correct sorted ballot, something like that. If you can call correct sorting as correct operation, you know what I mean, right? Or I could call it unlimited sorted ballot. I guess it would be better. Unlimited sorted ballot or something like that. So, and this contract is not going to have a limit of how many words I can process. I could process the whole dictionary here. I could process the whole Bible, the whole compendium of words in the whole history of humankind, and still I would be able to organize them from A to Z in a smart contract. Okay, so imagine you want to do a big operation, you want to sort other blobs, you want to filter submissions, whatever. You can use the same technique. We are going to create a lot of state variables for the things that we had in memory. Let me do like this. Put them side by side. So here in the function sort proposal that we had in the sorted ballot, I'm also going to have this sorted proposal here, but I have created the state variables for the proposals I already have. The line 10 is the same line 10 here. But now I have state variables for everything that I will need within the sort proposals functions. For example, I'll keep a separate array of proposals being sorted. Why? Let's go back for the article. We want to leave the contract operational after each atomic operation. We can't leave the contract in an unacceptable state between one swap and the other. So we are going to start the operation in block 1000, and we're going to finish the operation in the block 1100. If I use the proposals arrays in the middle, the proposals could be swapped. I want to vote for candidate 1. Oh, wait, now that is candidate 3. Oh my God, now is that candidate 2. I would need to keep track of these proposals juggling back and forth. Will be crazy. So I'm creating another array proposals being sorted. I'm going to initialize it in the constructor. This is also very gas intensive. This is not super optimal, but the objective of today's lesson is not gas optimization. It's just implementing amortization of work as a solution. So I create this proposal being sorted to keep track of this side parallel operation. I'm creating a functional state variable for swaps, sorted words, and saved index. That are the memory variables that we had inside the function. So the variable I in the line 19 became the state variable saved index in line 14. The variable swaps that I had in the line 20 became swaps, the state variable in the line 12. Okay, and the swaps that I have here 0 in this break condition is going to be used for calculating the sorted words, so that I can determine if the smart contract is sorted or not, if the sorting has finished or not, if my sorted words equal to the proposal length. Whenever I sorted all of the proposals, I can stop processing. Okay, this is going to spend much more gas. Yes. I also suggest that we put a function for restart sorting. It's not that necessary. And of course, we would put some guardrails here of only Allen or something like that, but it's good to have. If you are in the middle of this process and you use a step that is too big or something went wrong with the process, you can't recover, you have denial of service. Somehow you fell in that condition of denial of service. We had it here a while ago. So if you eventually fall in this condition of the denial of service with block gas limit for something that you did, it is good to have that option to restart from the beginning. Okay, I picked the wrong parameter or something wrong happened. I'm going to start from zero and then start from scratch to avoid denial of service. And then I have this sort proposals operation. It's going to do the same thing as I had in the sorted ballot, but now I'm passing some steps as parameter. The sort proposal would go from beginning to end without caring of the gas limit. Now I can receive this parameter of step, and whenever I get to the end of the amount of steps that I have passed, if my current step is higher or equal to the number of steps that I specified, I'm going to return and finish the execution of that function. Okay. This pattern, this boilerplate, this initial state can be copied for any loop that you want to do in the future. At the end of this operation, this is going to happen only once. You would offset the result of the thing that you want to do, this loop, calculate winner or pick best bet or something like that. You offset that to the return. Okay. Here we are sorting an array. So this operation line 38 is very big. It's gas intensive. It's not ideal. But if you are doing something more serious, like picking a winner in a auction, it might be just saving one number, like ID of the winner, something like that, you know. So it is easier to do that without consuming too much gas. Here it's more tricky because we need to copy an array from another array. You could do amortization of work for that too, but for now, this is good as a visualization. Okay. Now inside this to do, you code your logic. We have two cases, if this or if that. So I'm going to put those two if scenarios here. If I am at the end of the array, I'm going to do this. If I am at the beginning or the middle of the array, I'm going to do that. Browns, you want to ask something? I saw you raise your hand. I guess his connection fell. Okay, in the meantime, any questions here before we do this to do? We don't want to go it all at once. We want to do like 10 steps at a time or something like that. So I'm going to pass this number of steps and we're going to complete this gradually. This solution is here at the README, so you don't need to bang your head against it too much. We're going to do two ifs, okay? If I am at the end, I'm going to do this, else I'm going to do that. We copy this block and then delete to explain. Okay, so if I hit the step limit, I'm going to return. If I am at the end of the array, I want to do something. If I am in the middle, I want to do something else, right? In the past implementation, I was doing both at the same goal, as the same step. I do not recommend doing that because in the worst case scenario, if each of those steps would consume 20 millions, you don't want to process them in the same goal. Would do if this, consume one step, and then else that, consume another step. So you don't combine both operations in the same. If I am at the end of the array, I want to do this. If I am in the middle of the array, the beginning or the middle of the array, I want to do that. Let's convert this together. We have the solution too. Okay. So basically, if the swap equals to 0, how to know? I can be in the middle, I can be in the end, I don't know. So instead of calculating the swaps, I can calculate the sorted words. So if the sorted words is less than or equal to the proposal being sorted, I'm going to do this loop. If the sorted words is equal, I'm going to skip this while and I'm going to do the thing that is at the end. This is why I'm going to calculate the sorted words like this. Is the number of proposals being swapped minus the amount of swaps that I did. If I'm sorting 100 words and I did 10 swaps, probably not 90 of those words are in the correct place or closer to the correct place. If I have 100 words and I did 0 swaps from beginning to end, it's because I have 100 sorted words already. Okay. Swaps is 0, it's the same name. Instead of I'm going to put the saved index. And now every time that I reach the end of the array, I'm going to calculate the amount of sorted words, and then I'm going to reset to the beginning. If the amount of sorted words is equal to the proposal being sorted length, I can stop this while and save the state of proposals equal to proposal being sorted. Okay. Questions up to here? If you have a question, raise your hand, stop me. I can, yes, then.
So, if if the steps is greater than you already done, or that are we've already been through, then it it continues because it's thinking, okay, well, um, we haven't finished them all, or we haven't completed, and then else would be okay, we've completed, we can move.
Yeah, you're asking about the sorted words or you're asking about the step?
So for the sort proposals function, you know how it says that first, while something, if this, then, or else that, you're is I think
Here,
you might
right?
have switched it up just now. Yeah, there you go. So basically, if we've done some steps, but the current step is greater, we continue. Else, it seems like it's complete. The job's complete, so we can move on. Is that what's going on there?
Yeah, but it's not steps. Is this all the variable called sorted words actually? If the count of the words that we have sorted is equal to the amount of proposals that I have been sorted, I don't need to do any operations anymore. I can just finish that while and then do the line 46. Okay. The step is another limit. There are two possible things that are going to stop me from progressing in that loop. Either the step hit the limit of steps, and then I need to call it function again, or this amount of sorted words is equal to the amount of words that I want to sort, and then I finish the execution too. Okay?
Cool.
Two
Understood. Thank
possible
you.
break conditions here. And the only missing piece is what to do when we are in the middle of the array. So when we are in the middle of the array, we compare the previous object. If it's less than or equal to the next object, I do the swap. Exactly what we have here. So if in the else condition, let me copy this, I have the previous object, is the proposals being sorted, saved index -1. This is the same previous object as we had here. Okay, I guess I forgot to copy this. I will copy it all. I copied only the inside. Maybe this is causing the confusion. Sorry about that. So if the previous object is of the name is valid with the number equivalent of that name higher than the one that is after, then we need to do the swap, right? The only thing that I'm going to change here is proposals to proposal being sorted and I to save it index. Let me compare those two. Look, the previous object is equal to proposal I minus 1. Now the previous object is proposal being sorted, saved index minus 1. Previous object dot name, proposals I dot name. So previous object dot name, proposals being sorted, saved index dot name. The only change that I'm doing back and forth here is changing from proposals to proposal being sorted and from I to saved index. Then I can copy back and forth just as we had. Okay, and this is the solution. This would solve that smart contract for sorting 400, 500 words. Okay, let me test this in a script called test big loop or something like that. Unlimited. And it's not actually unlimited, we still have limits, but test loop, test big loop, whatever. That's not a great name, but you got the point. So I'm going to put this script there, which is going to do something very similar to the last script. But now I'm going to deploy this all the smart contract, the correct sorted ballot. Let me compile everything. I'm going to deploy this correct sorted ballot, and I'm going to test with 300 words. 300, more than double of what we did with the last one. And the block gas limit increases to 36. The last time I did this lesson. So let me run this here with this other script. Test bigger loop. And you're going to see that now we don't have a limit anymore. We would go block by block, saving the state of this operation. This loop can be picking a winner or something like that. We are sorting like 189, 203, 215, 234, 252, 265, 273. We are doing block after block, doing more of this calculation. And at the end, we might have used a dozen of blocks, like 8 blocks worth of gas for this operation. At the end, we paid in average a block price, we would pay more than half of one ETH, more than $1,000 by processing this transaction. But at least we don't have a limit. We could be validating a data set, speaking about artificial intelligence now. We could be doing a very heavy computer intensive job, occupying the blockchain for several blocks. But if we have to do, we can do it now. If we really, really need to do this for some reason, now we have the technique. Okay, and it can crash your computer, yes, it can crash the whole blockchain. You're pushing the limit. We still have a limit. Let's say we try to pass 2,000 words. It's going to break at the constructor function, but at least the loop is safe. Now we have effectively applied amortization of work, and we can properly process a limited amount of operations. Okay, not for sorting, but for any kind of actual loops, professional, useful loops that you need to do in the future. Okay, and that's it. I started the lesson 2 minutes late. ending 2 minutes late here too, but if you pardon me, the recording should be released by this week or so. Okay. Now my computer crashed, I guess. Okay, Arda, you want to do a quick question before we wrap?
Yes. What's the reason that we're not copying the whole proposals array to memory and working in our local EVM, sorting and then uploading?
Working on local EVM and sorry, I didn't get your question.
Yeah, so we're breaking this. Okay, I understand that you're trying to demonstrate what we shouldn't do anyway, right? Sorting on the blockchain.
Yeah, you should never sort on the blockchain. This is more an example for a loop. For example, you want to calculate the winner of an auction, and then you need to loop through all of the winners. You want to distribute dividends, and then you want to loop for all of the shareholders, something like that. Okay.
Yeah. So what my question is once again, why am I not? So I'm going to have to read the whole proposals array, right? At least the
Yes.
vote count, for example. So why am I not reading that into my local machine and work on my side and then publish the result later?
Yeah, because then anyone else using that result would need to trust you, right? The idea of the smart contracts, let's say you're going to pick a winner of that auction. I'm auctioning the picture of Mona Lisa, and I'm going to collect a lot of bets, and at the end I need to sell Mona Lisa to the highest bid. And I cannot do that off-chain and then offset the result because the result could be compromised. There are techniques that allow you to do that with zero knowledge proof, with roll-ups, with TEs and all. We're going to see more of those next week. For today, I'm showing you how natively inside the EVM, inside Ethereum, how you can do a loop that would surpass the limitations of the block limit.
All right, thank you.
Okay. Good. Thank you. I hope that you have enjoyed today's lesson. See you all tomorrow for more. Bye-bye.